Talked about solar radiation and terrestrial radiation, the sun giving off shortwave radiation, the earth giving off longwave radiation. Now we're going to talk about what the earth does with all of this. How does earth spin this? What is earth's energy budget? So that's what we're going to be talking about in this lecture. The goals for this lecture, first to understand how earth's land and atmosphere use solar radiation. Then we're going to talk about these special gases called selective absorbers and how they influence the greenhouse effect. And then we're going to talk about clouds and what they do to daytime temperatures and nighttime temperatures. You may be surprised. So without further ado, let's jump in. So first we're going to start with our sun. Our sun is really hot. And in fact, it's so hot that it emits a lot of radiation. Per the Stefan Boltzmann law from the last lecture, the warmer an object is, the more radiation it emits. And per Wien's law, the warmer the object, the shorter the wavelength. And this is true for the sun. So we call the radiation that the sun emits shortwave radiation. Now once the shortwave radiation leaves the sun, it travels a 93 million mile path to the top of Earth's atmosphere. Once it reaches the top of Earth's atmosphere, it continues towards the surface of the Earth. As it's doing that, one of two things happens. It's either absorbed by something or reflected and scattered by something. And let's talk about how this looks like. So, as far as absorption is concerned, about 70% of the radiation that reaches the top of Earth's atmosphere is absorbed. And it's either absorbed by the atmosphere and clouds, that makes up about 19% of the total solar radiation from the top of the atmosphere, or it's absorbed by the ground, and that makes up 51%. So for every beam of radiation that reaches the top of the atmosphere, that makes that journey from the sun to the top of the atmosphere, 19% of it will be absorbed by the atmosphere and by clouds, and 51% will be absorbed by the ground. The remaining 30% is reflected or scattered, and we're going to actually talk more about that 30% in detail in a few minutes, but for right now, 20 of that 30% is reflected by clouds, 4% is reflected by the ground and by the ocean. The ocean isn't nearly as reflective as you would think. And the remaining 6% is scattered. And this produces colors. So if you've ever wondered why the sky is blue, it's because molecules in the atmosphere scatter blue light very well. Hence, that's why the sky is blue. If you've ever wondered why clouds are white, they scatter all wavelengths pretty evenly. So clouds are nice and white. Well, this just shows you just the overall budget of what the Earth does with incoming radiation. 51% of it is absorbed by the ground, 19% is absorbed by the atmosphere, 4% is reflected by the ground, 20% reflected by clouds, and 6% scattered and reflected by the atmosphere. Again, we'll talk more about this 30% later. There's actually a fancy term I want you to know called albedo. But let's talk about absorption first. Some objects, like the surface of the Earth, absorb just about everything that hits them. So Earth's surface is a good example of this. The radiation that hits it, it absorbs. It doesn't really do a whole lot else with it. And it doesn't really absorb only certain wavelengths and reflect other wavelengths. No, it absorbs most of what hits it. A black t-shirt's another good example. If you've ever thought of a t-shirt that you're wearing or the clothes that you're wearing, the reason why they have the color that they have is because they absorb all wavelengths of visible light but that color. A black t-shirt absorbs all wavelengths of visible light. On the other hand, a white t-shirt reflects all wavelengths of visible light. If you're wearing a red t-shirt, then that shirt actually absorbs everything but red. and it reflects red, which is why it looks red. Same thing with blue. Blue t-shirt absorbs everything but blue. Green t-shirt absorbs everything but green, and so on. However, other objects or other gases or other things only absorb some wavelengths while being completely transparent to others. Think about the windows in your car. The windows on your car are transparent to visible light. That's a good thing because we want to be able to see everything outside of us. Otherwise, it wouldn't be safe to drive. But they actually are absorbent to other wavelengths of radiation. These are what we call selective absorbers. So think about selective listeners. I consider myself a selective listener. I only like to listen to the good stuff and ignore the bad stuff. Selective absorbers absorb some wavelengths and are completely transparent to other wavelengths. Greenhouse gases are a certain type of selective absorbers. They are transparent to most shortwave radiation, while absorbent, opaque, that's another fancy word that we use, opaque, to other types of long-wave radiation. And hence, they end up acting like a blanket in a sense. A transparent blanket, but a blanket nonetheless. They let sunlight in, but they don't let Earth's long-wave radiation out. Let's talk about these greenhouse gases a little bit more. As I just said, they're transparent to shortwave radiation. So the radiation that the sun emits, they are perfectly transparent to it. They let it just pass on through. On the other hand, the radiation that the Earth gives off, that long-wave radiation, is mostly absorbed by them. Now this is a good thing because this keeps us warm. And what this also does is it warms up those greenhouse gases in the atmosphere. As they warm up, they then emit more radiation. Again, the Stefan Boltzmann law. The warmer an object gets, the more radiation it emits. Some of that radiation is emitted back out to space. Other amounts of it is emitted back down to the ground, keeping us warm. So greenhouse gases keep us warm. Now, what gases absorb what wavelengths? Well, if you take a look here, this is what's called the absorption spectrum, and it shows you several different wavelengths of radiation here on the x-axis, and then the percentage of what they absorb here on the y-axis. So where you see a lot of gray, these areas represent areas of little to no absorption. Where you see a lot of this purple area, that represents lots of absorption. And as you can see here, nitrous oxide, completely transparent to shortwave radiation. Lets it all through, it absorbs none of it. However, as you get towards longer wavelengths, around 5 microns and around 7 microns, nitrous oxide is very opaque to those. It absorbs those pretty well. Hence, nitrous oxide is a greenhouse gas. Methane is very similar. Methane is completely transparent to most shortwave radiation. However, it absorbs a lot of radiation at 3 microns, 4 microns, and again at 7 microns. Oxygen also does a really good job of absorbing some long-wave radiation, specifically here at 10 microns and a little bit here at 15 microns. The difference between ozone and these first two is that ozone also absorbs tremendous amounts of ultraviolet radiation. Now that's a good thing. We like that because that prevents all that harmful radiation from reaching the surface of the Earth. So yay ozone. Water vapor and carbon dioxide down here, they also absorb a tremendous amount of long-wave radiation while being perfectly transparent to shortwave radiation. When you add all this up, what you end up getting is this down here. This is the absorption spectrum of the total atmosphere. And what you notice is that because of ozone, much of the ultraviolet radiation is absorbed. A little bit of visible light is absorbed. And then there are all of these wavelengths here in the long wave radiation that are being absorbed. There's one big exception. Between approximately 7 microns and 12 microns, and it varies a little bit from person to person, from textbook to textbook, but right around here is what we call the atmospheric window. With the exception of right around 9 to 10 microns, almost everything here passes back out into space. So these are the wavelengths that everything is pretty transparent to. So, and so that's something that we as meteorologists are really interested in looking at, because when we fly satellites over the Earth and we're looking at infrared radiation, these are going to be the wavelengths that we really want to look at. And we'll talk more about satellite and why that's important when we talk about mid-latitude cyclones. So that's coming up. Now, what happens to radiation that's not absorbed? Well, it's either transmitted, which means it just simply passes through a material. So all the stuff that wasn't absorbed either simply passes through, it's transparent, or it reflects off of that something, simply bounces off of that something. So when this happens, the radiation hits the object and then just bounces off of it. And that's what reflection is. Now, I mentioned earlier that about 70% of the radiation that reaches the top of the atmosphere is absorbed. The other 30% is reflected. And we call that 30%, we have a fancy name for it, we call it the albedo. So the albedo is the percentage of radiation that is reflected off of an object. And the average albedo of Earth is about 30%. Or if you're using whole numbers, decimals instead of percentages, it's 0.3. So it's about 30%. That means that 30% of the radiation that enters the top of the atmosphere is reflected back out to space. Let's talk more about this albedo, what it actually means. It represents how much light is reflected by an object. So for every beam of radiation that hits an object, how much of that is reflected back out? Well, you can actually identify the albedo of an object by simply looking at how dark or light it is. The lighter colored the object is, the higher the albedo. This is why when it's really hot outside, you will hear people say, remember to wear light-colored clothing today because it's really hot outside. The reason why they're saying that is because you want to wear stuff that's going to reflect most of the light that hits it. That way that keeps you cool. Otherwise, if you wear something dark-colored that has a low albedo, it's going to absorb all that heat. And that's going to heat you up. That's going to make you feel hot. So white objects have very high albedos. They reflect most of what hits them. Black objects have very low albedos. They absorb most of what hits them. So here are 3 circles here. We have a very brilliant white circle here, a moderately gray circle here, and a very dark gray circle here. In fact, on many of my screens in my classrooms, this almost comes off as pitch black. Well, the lighter colored the object, the higher the albedo. The more sunlight, the more visible light that is reflected off of it. So this white object is going to reflect most of the radiation that hits it. This dark circle would absorb most of it. So here is a table showing you the average albedos of different objects. Snow has a very high albedo, hence it looks very brilliant white. 75 to 95% of the radiation that hits snow is reflected off of it. Clouds typically are also very reflective. That's why when it's cloudy outside, it usually seems very dim, because most of the sunlight that hit the top of the cloud bounced right back off and went back out into space. On the other hand, the thinner the cloud, the more sunlight is able to break through. Here are a few other planets. Venus has a 78% albedo, Mars has a 17%, Earth has a 30%, and then these are just some other numbers. You don't need to memorize these. I just want you to just see them and just kind of know, okay, some objects have higher albedos, others have lower albedos. But here's what I would like you to know. Something like this, fresh snowfall. It's just brilliant, white, bright snowfall. This has high albedo. This is one of the reasons why when you go skiing, you want to wear sunscreen, because if you don't, your face is going to get burned from all that reflection that's hitting your face. On the other hand, with the exception of this little area here, most of this forest, this dense forest, has lower albedos. It absorbs most of the radiation that hits it. Now with that said, I've talked about the Earth absorbing and reflecting radiation, but how does this actually affect Earth's temperature? Well, think about your bank account, and let's say that the total balance of your bank account, that total number at the end, is the temperature. And think about the idea that each month you have income. If you're working a job, you're getting a paycheck, or if you're living at home, you might be getting an allowance or something like that. You have some kind of income. On the other end, you also have spending. Maybe you have a cell phone bill, maybe you have food, or you're going out to see a movie, and you have spending. Well, your income and your spending, the difference between the two is going to result in a change to the overall balance of your bank account, right? Well, Earth is the same way. Earth has income, and its income is from two sources. The first source is shortwave radiation from the sun. The second source is that long-wave radiation that was absorbed by clouds in the atmosphere. Remember, every object with a temperature above absolute zero is emitting radiation. So that's Earth's income. Now, I'll be honest with you, the incoming from the sun is by far the greater of the two. On the other hand, the Earth also has spending. It reflects shortwave radiation. It also, because the Earth has a temperature above absolute zero, it also emits long-wave radiation. There's a few other things that the Earth does with the heat that it receives, though. Some of it is then released into the atmosphere via conduction and convection. Another chunk of it is either absorbed or released by water as it's changing phases. That's called latent heat flux. Again, we're going to talk about this latent heat next week when we talk about moisture. And then finally, some heat is absorbed into the ground. That's called ground flux. So Earth has income and Earth has outgoing. And Earth has a balanced budget. If you actually totaled these two things up, you would be surprised to find that they're equal to each other. Income equals outgoing. Earth's budget is balanced. Incoming equals outgoing. Now think about this with your bank account. If your income is equal to your spending, how is your balance going to change? How is the amount in your account going to change? Well, it's not going to change, right? If your income equals your spending, your total balance does not change. On the other hand, what would happen if your income became greater than your outgoing? And there's one of two ways that can happen. And we'll talk about those in a later video. Well, if your income was greater than your outgoing, that means that you're making more money than you're spending. Your bank account would increase, it would grow. On the other hand, if the amount of radiation going out was greater than the amount of radiation coming in, then your bank account would shrink. Well, what happens with Earth? If income is greater than outgoing, Earth will warm. Earth now has additional heat. It's absorbed that additional heat, therefore it has a higher temperature. On the other hand, if the income is less than what's going out, the Earth would cool. And this actually does happen on a day-to-day basis. During the daytime, incoming is greater than outgoing, and so the Earth warms during that time. At night, incoming is less than outgoing. In fact, incoming is oftentimes close to zero, whereas outgoing is still happening because, again, the Earth has a temperature above absolute zero, so it's still emitting radiation. This means that the Earth is cooling. This also happens with different latitudes. So let's talk about latitudes for just a quick moment. A latitude simply means the distance in degrees from the equator. So if you took a look at a globe, the equator is that belt that wraps around the middle of the Earth, halfway between the North Pole and halfway between the North Pole and the South Pole. It's usually very warm there. Meanwhile, the poles are on the northern end and the southern end of the planet. So the equator's at 0 degrees, the poles are at 90 and south. The sun is almost always overhead at the equator. As a result, places near the equator get a lot of heat. Don't believe me? If you took a flashlight and you shined it straight down, what you would get is a tiny circle of that's very, very bright. Why? Because that sunlight is concentrated over that area. On the other hand, if you're near the poles, the sun is coming in low on the horizon. In this case, the sun is actually spread out. That sunlight spreads out over a larger area. As a result, it's more dilute. So regions near the poles get very little heat. This actually creates an interesting concept, and here's just an image of this. If you live near the equator, the sun is overhead. As a result, it's spread out over a small area. Therefore, it's very concentrated. Meanwhile, near the poles, the sun is very low in the sky. When it hits the ground, it spreads out over a larger area. And therefore, it's more dilute, hence it's cooler up there. Well, you end up getting an interesting result where near the equator, you actually have more sunlight coming in, more shortwave radiation coming in than going out. So ideally, this region here near the equator should actually be warming up. On the other hand, if you live near the poles, you actually have much less radiation coming in than you do going out. Here, you would expect it to be getting substantially colder. However, as I said in a previous video, Mother Nature doesn't like imbalance. As a result, surplus heat is actually transferred from near the equator to higher latitudes. How does this happen? We're going to talk about it in several weeks when we talk about global circulation. But this right here is one of the single greatest causes of all of our weather, this imbalance of heat. The last thing I'll talk about for this lecture is clouds. Now, I'm sure it's pretty obvious that when it's cloudy outside, it's usually cooler than it would be if it was sunny outside. All things else, humidity and so on being equal. When there are clouds overhead, that means less sunlight can get down to the ground. And therefore, just by principle, it's cooler. But what people actually don't understand, or what people don't actually know, is that's only true during the daytime. Because during the daytime, the sun's out. And those clouds are highly reflective. And so they reflect much of the sunlight that hits them. doesn't make it to the ground, therefore it's cooler. However, at night, there's no sunlight. Sunlight is not coming in. However, remember, the Earth is giving off its own long-wave radiation. And those same clouds that were so reflective to short-wave radiation during the daytime are also very absorbent to long-wave radiation. So they are reflective to short-wave radiation, but absorbent to long-wave radiation. This actually heats the Earth up at night. So these two effects greatly influence how clouds affect Earth's temperature. During the daytime, the albedo effect is key. Clouds reflect much of the sunlight, keeping the Earth cool. On the other hand, at night, because there's no sunlight coming in, albedo doesn't really matter. Instead, it's the cloud greenhouse effect that greatly influences nighttime temperatures. Radiation that the Earth is giving off is absorbed and emitted back down by clouds, keeping the Earth warm. So, the cloud albedo effect, simply during the daytime, clouds have a high albedo, meaning they reflect much of the sunlight that hit them. This prevents that sunlight from reaching the Earth, cooling the Earth down. So cloudy days are cooler than clear days. On the other hand, at night, there's no sunlight coming in. So there's no albedo. Albedo doesn't matter at night. But Earth is always giving off long-wave radiation. Clouds absorb that radiation, emit it back down, and the Earth warms. So cloudy nights are warmer than clear nights. And you can actually see this. The next time we have a rainstorm or like a really rainy day or a really cloudy day, look at how the daytime high and the nighttime low temperature change. What you'll actually find is on those particularly stormy days, the temperature doesn't really change much. On the other hand, wait for a clear day, and you'll notice that the high temperature during the daytime is usually a lot higher than the temperature at night. And this is, again, because you have that influence of clouds that make daytime cooler, nighttime warmer, and so you have a very small temperature range. So, just to review really quickly, incoming shortwave radiation is either absorbed or reflected by the Earth's atmosphere, and it's approximately 70% absorption, 70% reflection. Gases can be selective absorbers, meaning they're transparent to some wavelengths, but absorbent to others. Greenhouse gases are a good example of this. Greenhouse gases are transparent to shortwave radiation, but they absorb long-wave radiation. And then finally, this whole albedo thing, albedo is simply the percentage of sunlight that's reflected by something. Earth's albedo is around 30%. So that's it for this lecture. The next lecture we're going to be talking about how incoming sunlight changes throughout the year and how that affects our seasons. So join me next time for that. Until then, I'm Terrence Mullins. Thank you for watching.